Okay, so we've started going back over some of the homework from last week. I guess, Oliver, I'm going to get rid of your work really quick. And we'll just do B from scratch and keep going from there. So we had this metal wire that's heated at one end, and we've got temperature in degrees Celsius of the wire from the heated end at different distances. With a twice differentiable function, we're on part B right now, where we want to write an integral
Yes.
expression. So what we're trying to estimate is this. We're trying to estimate the average temperature of the wire. So my average value formula would be 1 over 8 times the integral from 0 to 8. So that's 1 over b minus a, 1 over 8 minus 0 of our temperature in terms of x. And they want us to do it using a trapezoidal sum with 4 subintervals. So that trapezoidal sum means I'm going to take trapezoids that have different heights and add them together.
Yes. But how do I know that it's trapezoids?
Because they told us that this would be a trapezoidal sum. So we need to use trapezoids for our shape.
Okay.
If they tell you it's a left-hand Riemann sum or a right-hand Riemann sum or a midpoint Riemann sum, then you can assume we're just using boxes. But if they give you trapezoids specifically, then we've got to use trapezoids. Okay, so for a trapezoidal sum,
Oh, okay.
I'm gonna write our bases really quick. So this is a base from 0 to 1 is 1. A base from 1 to 5, I'm going to make this a little bit bigger maybe. Okay, so I've got a base of 1 with heights of 193. Cool. So I've got our trapezoidal Riemann sum. Make a mark just so I know when this started back. Got our trapezoidal Riemann sum here with our distances between each space. If I wanted to find the area of this trapezoid, what would I have to do? Testing, 1, 2, 3, testing. Hello, can you hear me?
No. Yeah. No, it's fine.
Okay. Well, let's try this again. Sorry about that. Okay, so I've got our trapezoidal sum here.
Okay.
If I wanted to get the area of this first trapezoid, what would I do?
Um, one side times the height divided by 2.
Okay, so I'm going to sum these two heights together and then divide by 2 to get my average height. And once I've got the average height, we can multiply by the base. So my first triangle would be 100 plus 93 over 2 for the average of my heights times 1. Okay, what would the second trapezoidal be?
Why is it divided by... Oh, okay. 93 times plus 10.
Okay, 93 plus 70 over 2 times my base,
Step 4.
4. Plus, okay, I'm going to do the same thing, 70 plus 62 over 2 times 1. Plus, this is 62 plus 55. over 2 times 2. Okay, then to get my area, I'm going to add all of those up. So I think I'm going to keep these over 2 for now. So this will be 193 over 2 plus this is 163 times 4 over 2 times 4 over 2 plus 132 over 2 plus this is 117, I believe. Right. Okay, I guess I am going to simplify then from this step instead of just adding them all together. So I've got 193 over 2 plus my 2's will cancel, so I've got 6, 2, 1, 326. This is 66. Blanking out today. Okay, so 117. Then I can add them all together. So if I keep going with this, I'm going to get my A, and then my average temperature is 1/8 of that. So I could say 1/8 of A would be equal to this. 183 over 2 plus 326 plus 66 plus 117. Okay, divided by 8 is 75.6875. Which again is my estimate. So my approximation of my average value of our temperature. Okay, so there's everything together. Any questions on B?
No.
Okay, cool. I think I'm going to copy this whole picture again, and we'll do C on a separate page. Oop. Okay. So then I want to find the integral of the derivative of t and indicate units of measure, and then explain the meaning in terms of the temperature of the wire. Okay, so you said you weren't sure on this one, right?
Yes.
Okay, so if I integrate a derivative, what will happen? So,
FB minus FA.
right, so when I integrate t prime, I'm going to get t of 8 minus t of 0, right? So then I can go up here and figure out what our temperatures were there. T of 8 was 55 and T of 0 was 100. So that's 55 minus 100. Or negative 45 degrees Celsius is equal to the integral from 0 to 8 of T prime x. dx.
But what does it say in terms of the temperature of the wire? That the wire gets colder and colder until
Yes.
it reaches. Okay.
So this is temperature has dropped by 45 degrees Celsius as we move from the heated end of the wire at 0
Okay.
to the 8 centimeter mark. Is that the end of the wire? I didn't actually read this carefully. Yes, to the other end of the wire then. So I could write something like the temperature
Drop.
Yep. Temperature of the wire drops by 45 degrees Celsius from the heated end to the other end. Okay, and we did indicate units of measure and explain the meanings. That should be good. Any questions on C?
No, that was clear. This one.
Okay, cool. Then the last one for D. I want to know if the data in the table is consistent with the idea that the second derivative is positive for every x on our interval, and then explain the answer.
How can we find t prime prime?
We can't find t prime prime directly, but we can get some information about our slopes, and that could tell us whether or not the slopes are
Okay,
constantly decreasing. So, how could I get information about the slopes?
set the prime equal to 0. T prime.
Okay, so the problem is we don't have a function, so we can't, because we don't have a
Oh.
function, I can't just set the function equal to 0. But if I wanted to talk about change in temperature, sort of like what you did in part 1, how could I get an estimate for the changes in temperature?
FB minus FA over B minus A.
Okay, so I'm going to do that for 2 of these intervals, and we'll see what we can come up with. So I'm going to pick these 2 numbers in the middle. And we'll take a look at our change in temperature from 1 to 5, and our change in temperature from 5 to 6, and compare them. So that gives us...
We can see that it's already increasing, or?
we can see that it's decreasing, but I want to know if the decrease is increasing. Does that make sense?
Oh, okay.
So we're talking about the slope of the slope for our concavity. So I need to find the slopes first, and then we'll see if we can compare the slopes. So if I do, we had a distance of, so this will be average temperature from 1 to 5 is, I'm sure there's a better way to write that, but is equal to 70 minus 93 over 5 minus 1, which would give me 5.75, and it's going to be negative. So that was negative 23 over 4. So the 20 over 4 is the 5, and the 3/4 is 75. Okay, then I've got my average temperature from 5 to 6. Okay, now what I'm looking for here is if this average temperature from 5 to 6 ends up being...
Is higher or lower?
Right, I'm just looking to compare these 2 average temperatures. So if my average temperature decrease was different, Okay, so this is 6 minus 5 on bottom, and 62 minus 70 is negative 8.
So it
Okay,
increases.
so my rate of change actually decreased on those two intervals, right? Which means the
Yeah.
slope of my slope was negative, which means this is not true. Our concavity could not have been positive. Okay, so I'm going to see if I can explain really quick. Hmm. The average rate of change on the interval 1 to 5 is negative 5.75 by the mean value theorem. T prime at C for some C on 1 to 5 must equal negative 5.75. And the same thing for this one. The average rate of change on 5, 6 is negative 8. Therefore, T prime C, I'm going to do another variable, T prime D equals negative 8 for some D on 5, 6. As T prime decreases, from C to D, T prime prime is not positive for all x on interval 0, 8. Okay, that was a fairly long explanation on my part. I'm sure there's a faster way to do that, but that should prove it. Any questions on what we did?
So it just says that it's increasing more or like faster.
It's we're actually not increasing, we're decreasing, but the rate at which we're decreasing.
It increases.
Right.
Okay. Right.
Okay. Any questions on this one?
No.
Cool. All right. I'm gonna really quickly run through 2 or 3 integration techniques, and then because we're kind of out of time, I'm gonna leave it up to you for whether you want to stay for the older ones or not.
Okay.
So we're going to be looking at integrating functions with a bunch of techniques, and then I've got these two in the part that is not new, with partial fraction, decomp, and long division. So if you want to stay for those, you can. If you want to just read those on your own, I'll leave that up to you. But I do want to look at 2 of these that we had trouble with on the midterm. So specifically, integration with absolute values and integration with piecewise functions, which have been tricky for us all year, I think. So When we're integrating with absolute values, the key is, because integration is really just repeated addition, I can break these apart. And then whenever this absolute value part would be negative, I can split up that interval where that area would be negative and just multiply that total area by -1 to make it positive. And I would get the same thing as taking the absolute value. Does that make sense?
Yes.
Okay, so here's what it looks like. I'm going to break this apart, so my x and absolute value part into two separate integrals, and just leave that over here for now. So we're not really worried about this part. Okay, then for our absolute value part, because this 2x without the absolute value will be negative as long as x is less than 0, I'm going to break this apart into an interval from -2 to 0. That's the part that would be negative for my area, right? And multiply that by -1 to make that area positive. Okay, this part from 0 to 2 is already positive, so I don't need to multiply it by -1 and it will stay positive. Does that make sense?
I don't understand why we have to multiply by -1.
So the idea here is that without the absolute value, when you integrate from -2 to 2, part of our area, so from -2 to 0 is going to be negative. So this area
Yes.
1 is going to be negative, right? But because I want to simulate the absolute value here, I want to integrate the absolute value, which means I really want to make that area positive, which we could do graphically pretty easily, right? But to do that by hand, you would take that same area that you would have gotten that was negative and just make it positive by changing the sign. To change the sign, I could multiply by -1.
Okay, I see.
Okay, but for this part that's already positive, we don't need to multiply by -1
Yeah.
because it's already positive. So this a2, we're just going to leave the same. So what we've done is we've split the interval into the negative part of the area and the positive part of the area. And then we've just taken the negative part of the area and multiplied by -1.
Okay.
Cool. So that gives us, now we've just got a normal integration problem. We can solve this with integration's power rule. So I'm going to add 1 to the power, divide by the new power, is x squared over 2 from -2 to 2. This one is -2x, so that'll give me -x squared from -2 to 0, and this one is 2x, so that'll give me positive x squared from 0 to 2. Let me just do upper bound minus lower bound, so that's 4 over 2 minus 4 over 2 is 0. 0 minus -4 is positive 4, plus 4 minus 0 is 4. So I've got 0 plus 4 plus 4. I can't write a plus sign. 0 plus 4 plus 4 is 8. Any questions on what we did here?
No.
Okay, that was really fast. That was good. For piecewise functions, we do almost the same thing. So this piecewise function is defined as two separate functions when x is less than 3 or when x is greater than 3. So what I'm going to do is, because integration is addition again, I'm just going to split f of x. So the integral from 1 to 7 of f of x will be the same thing as the integral from 1 to 3 of my top function, plus the integral from 3 to 7 of my bottom function. I feel like this is easier than the absolute value one, but do you understand what we're doing?
Yes.
Cool. So then after I split this, we're just going to integrate normally. So again, with power rule, this is -x squared over 2 plus 3x, and then I'm going to plug in my upper bound minus lower bound. This one will be x squared over 4 minus 3 halves x from 3 to 7. Plug in my upper bound, so this will be -9 over 2 plus 9, minus -1/2 is plus 1/2, minus positive 3 times... Oh, I feel like that should have been a 3. Did I do this wrong? Where did I go wrong? -3, -1. Okay, then that would give me -8 over 2 is 4. Okay, I may have to redo this from this step, unfortunately. It'll break out. And we'll zoom in and start from here. Okay, so I plugged in, this is -3 squared over 2 is -9 halves, plus 9. Okay, I'm walking through so you can check me. I've got negative 1/2. If I'm subtracting that negative 1/2, it would be positive 1/2. And this should be positive 3, and if I'm subtracting, it would be negative 3, right?
Yes.
Okay, cool. Now check me on this side. So this is 7 squared is 49 over 4. Minus 3 times 7 is 21 over 2. Okay, minus, this would be 9 over 4 again. And then I'm subtracting a negative, so that would become positive is 3 by 3. Should be 9 over 2.
Yeah.
Okay, cool. Then we need to add up. Okay, so if I add these up, this is my 9 minus 3 is 6, and then I've got negative 9 over 2 plus 1/2 is negative 8 over 2 is negative 4, so this is 6 minus 4 plus, I've got 49 over 4 minus 9 over 4 is 20, is 40 over 4, or 20 over 2, or 10. So that's plus 10. And this negative 21 over 2 plus 9 over 2 is going to give me negative 12 over 2, or negative 6. Yeah. Sorry, there's a little bit of a delay with Skype. Okay. So I've got 6 minus 4 plus 10 minus 6 is 6. Okay, look good to you?
Mm-hmm.
Okay, I did check the final answer, but I did have that process mistake, so looks good. Alright, so I have a handful of other integration techniques. I'm going to leave you an option. I can either run through them as quickly as I can now, or I can give you the paper and let you read on your own. It is something we've done before. Would you like to stay for another 15 minutes or so and run through the other integration techniques?
Yeah, sure.
Okay, cool. So, let me pull those up then. So I've got a handful of integration techniques from quarter 2. Okay, starting with u-substitution. So the idea with u-substitution is to undo chain rule. So I'm going to be looking for what part was our inside function. I'm going to substitute u for that, and then our derivative will be u prime. That'll allow us to rewrite in terms of a new variable. Okay, so here's my example. We're integrating from pi to 3 pi over 2 of sine x cosine x dx. I'm going to write my dx over here. dx. Okay, so that means if I say my inner function is sine x, then my derivative of that function would be cosine x dx. So this would then be u times u prime, right?
How do we know that u is not cosinus x?
We could use u as cosine. In that case, the u prime would be negative sine, and dx,
Okay.
and I would need to have a negative on the outside. So for this one, that would still work. I'll take a look at another one where it'll matter which one we pick, but sine and cosine are a little bit weird in that when you derive them, you get the same thing.
Yeah.
Okay, so just with different signs. Okay, so if I say u is sine and u prime is cosine dx, then when I substitute, this would be u times u prime, right? Now, there's two ways of doing this. You could ignore your bounds, integrate, rechange everything back in terms of x and plug your bounds in. Or you could change your bounds. If u is the sine of x, and this was originally pi, then u would be the sine of pi, which is 0. If this was 3 pi over 2, and u is the sine of x, then the sine of 3 pi over 2 would be negative 1, so a new bound would be negative 1. And now I'd never have to change back in terms of x. I can just integrate normally here, in terms of u, and I would get the same answer. Okay, so if I integrate u times u prime, I'll get u squared over 2. Again, every time you're going to divide by dx and add 1 to the power, divide by the new power. So this will be divide by u prime, and my u primes will cancel. Add 1 to the power will become 2, and then divide by the new power is divide by 2. Okay, so I've got u squared over 2 from 0 to 1, 0 to negative 1. So I'm going to plug in negative 1 first. That's negative 1 squared over 2, and then subtract 0. Gives me 1/2. Okay, so the advantage of doing this is, first, it's going to help you on your multiple choice for the AP exam, because a lot of times there's a multiple choice question where they're trying to match what's happened after they've rewritten that integral, just because they know some students skip this step. And then second, it makes your work right on the process for the free response, so you don't have to kind of awkwardly leave out your bounds. So you may lose points if you will lose points if you write your integral with the wrong bounds, so with x bounds like this, but then write u's. That's not correct because your bounds are not in the same variable as what your integral is. So if you do it this way, you don't have to be careful with not writing bounds for your intermediary steps and your free response. Okay,
Yes.
any questions on what we did for u-sub?
No.
Okay, I'm not going to run this one all the way through, but I am going to look at what my substitution is. So my substitution for this one must be the bottom part. That way my u prime would be on top. Okay. Long division. So we're going to use long division for polynomials anytime that we have an improper fraction. An improper fraction is whenever your power is larger on top than it is on bottom. So that's my cue to use this. So for this one, this is, I'm dividing x cubed by the polynomial x squared plus 1. So if I multiply x times x squared, I'll get x cubed. If I multiply x times 1, I would get x. So I can subtract x cubed plus x from x cubed, and I would get 0, x cubed minus x cubed, which you don't have to write. And then minus x. There's nothing I can multiply x squared by that would give me minus x evenly. So that means my remainder can just be written as negative x over x squared plus 1. Okay, so this is equal to my original x cubed over 1 plus x squared. We've just broken this apart, which means I can integrate. So if I wanted to integrate this total x cubed over 1 plus x squared, my original function, that's the same thing as integrating x plus negative x over x squared plus 1. Again, because I'm adding, I can split that up into two separate integrals, so this one's easy with just power rule, but this one, I could integrate using u-substitution. Okay, I'm not as concerned with the integral part because we've done the integral part already, but are you okay with the long division process?
Yes.
Okay, I guess I'll finish this one out because it's here, but my u-substitution, u would be x squared plus 1. U prime would be 2x dx. So I've made that substitution here. I only had an x here. I had a negative x here, so to get to 2x, I'm going to multiply by 2 and divide by 2. So I can pull that out. That gives me what I needed for u prime and u. We make our u substitution and integrate. Any questions on this one?
No.
Cool. Okay. Then completing a square. So this has been a little bit tricky for students in recent years, mostly because I think when you guys are factoring, both of you prefer quadratic equation to completing a square, which means we don't have a lot of practice with completing a square in general, but the idea with completing a square is we're going to try to make a perfect square out of a quadratic. So starting with this, I've got 2x minus x squared on bottom. I'm going to multiply through by negative 1 just to move my x squared in front. So for this x squared minus 2x part, if I wanted to complete a square, I could take my middle term, divide by 2, and square it in order to complete a square. So negative 2 divided by 2 is negative 1, squared is positive 1. So that gives me x squared minus 2x plus 1. Because I added 1, I also have to subtract 1 in order to not change the problem. Okay, the reason why we did that is because this x squared minus 2x plus 1 is a perfect square, is x minus 1 squared. A perfect square is when you factor, you get the same factor twice.
Mm-hmm.
Okay, so that means inside my root now, I've got the negative 1 that we pulled out, the perfect square that we just found, x minus 1 squared, and then the minus 1 that I had originally because we added 1 to that problem. So now I'm just going to multiply everything back out to figure out what our problem is now. So if I multiply my negative 1, that changes the sign on both of these. So that leaves me with this. Okay, so now I can do a u-substitution where u is equal to x minus 1 and u prime is equal to dx, which would give me this, which is now in the perfect form for an arc sine function if I wanted to integrate. The integral of du over root 1 minus c squared is arc sine u plus c.
Okay.
And then I can resub for u as x minus 1, and I've got our final answer. Any questions on what we did?
No.
Okay. Again, going a little bit fast, but we've seen these before. I think, second to last one. Okay, so we've got partial fraction decomposition. So the idea is, if I was going to add two fractions that did not have a common denominator, I could cross multiply to give them a common denominator and then add the numerators, right?
Mm-hmm.
So if I wanted to work backwards, I wanted to start here and break it apart into smaller parts. Then what we could do is I would factor the bottom first. Do I do this down here? Yeah. Okay, so I'm going to factor the bottom first. This is x times x plus 1. And I'm going to assume that there are some factors we have not found yet, a over x plus 1 and b over x, that we could split this fraction into. Then using the same process, in order to get my common denominator, I would have to cross multiply. So I'm going to multiply a times x and b times x plus 1 in order to get my common denominator. And I would add the numerators together to get my final answer, right? So this means 3x plus 1 should be equal to a times x plus b times x plus 1.
Yes.
Okay, and then I can use any techniques you want in order to solve for a and b. A and b are just constants, or coefficients. So I could group these and say my only constant is b right now, so b must equal 1. And then a plus b must equal 3 because my coefficients of x have to equal each other, right?
Mm-hmm.
So if 3 is a plus b and b is 1, then a is 2. Okay, then I can go back in and plug those in. So this was a over x plus 1 is 2 now over x plus 1, and then b is 1, so that's 1 over x. So if I wanted to integrate 3x plus 1 over x squared plus x, I could instead break this apart into its partial fractions and integrate. I'm going to move this 2 out. So this would be 2 times the integral of 1 over x plus 1 plus integral of 1 over x, which would give me 2 times ln x plus 1 and 1 times ln x. Any questions on what I did?
No.
Cool. Again, fast, but we've seen this once before. Last one is solving for x in terms of u. Now, normally with u substitution, we would want our derivative of u, our u prime, to be 1 power less than what we started with. There are exceptions, such as the arc trig integrals that we saw earlier, so arc sine, arc secant, arc tangent, where our derivative of u ends up being 1 less than half the power of our original u. But when both of those aren't possible, we don't have 1 less than half the power in a fraction, which is our q for an arc trig function, and we don't have 1 less than the power of our normal u for the inside function, which is our q for u substitution. Then what we can do is we can try to rewrite our fraction in terms of u. Here's what it looks like. So for this one, I've got an inside part of this fraction that has to be 2x minus 5, right? When I derive that, I get 2 dx, which is not what I have for my power on the outside. So what I'm going to do is I'm going to take my function that we just created for u. U is 2x minus 5. And I'm going to try to rewrite it for x and see if I can substitute. So if I do, this will be u plus 5 divided by 2 is equal to x. So now I'm going to take this x. U plus 5 is equal to u plus 5 over 2 is equal to x, and substitute that for x in my original equation. I'm going to substitute my 2x minus 5 for 2x minus 5 in my original equation, and I'm going to substitute 2 dx. So 2 dx for u into my dx here. Okay, so here's what it looks like. I have 4 dx right now, so that's 2 dx times 2, which would be 2 times u prime. I have an x, which I could replace with u plus 5 over 2, and I have 2x minus 5 to the 4th power, which I could replace with u to the 4th power, Okay, my 2 and 2 will cancel, and then I can distribute. U to the 4th times u is u to the 5th, u to the 4th times 5 is 5u to the 4th. Now I can integrate using power rule. Okay, so I do u to the 6 over 6 plus 5u to the 5th over 5, or just u to the 5th if you want. And then because u is 2x minus 5, I can go back and resubstitute to get my final answer. Okay, so the trick here is when we do your original u substitution, you have created a function that you could solve in terms of x, which means if there's any x's left over in your original problem, you can use this equation that you've created, solve for x, and then substitute that back in for all of the x's that were left over in your original equation in order to get it rewritten in terms of u.
Okay.
All right, any questions on anything from today?
No, it's clear.
All right, thanks a lot for staying over time. I've got a handful of homework problems that I'll be sending on Skype, WeChat, and course sites again. So thank you.
Yeah. Thanks. Bye.
Goodbye.